right, so maybe I can edit this. I have a video editor. I can edit out that stuff that we didn't do. But this is the from this problem. Let's see, try to fix it. This is the problem that we're doing right now, but we're modifying it. Zach, if you can still hear me.
Yes, can you hear me?
That problem, and we're converting it to be a two-stage thing. We want to find out when B stops, or how the distance B stops. So, got it all set up. Stage 1, 2, and 3. Yeah, maybe I can edit out that other. I wasn't sharing my screen, so it's not being recorded. All the stuff we did. All right, so we go to potential energy 1, and that's just simply going to be
what happened last time?
not 1/2. It's going to be MGH1, if you want to call it H1. Right? Decided this is going to be H1 over here. So 11.5, 9.81, and 0.9. So I have that as 101.5. These are Newton meters. And then we have external losses because of the friction of this thing moving. We need to figure out how far this is going to move, though, because it's not going to move the same distance.
Let's hear it again.
So this is not going to move 0.9. It's going to move something. We got to think about it. I think it's going to move something more.
B is work.
Yeah. B is going to have some external work that's done to it because of friction. Because we're defining the system as all the pulleys and all the mass, the pulley and all the masses together. So I need to do a little bit of stuff.
So now exactly how? Because that's I didn't get either. Because a lot of how it works, there wasn't work. So on the equation sheet, we have the equations for KE and PE. So how exactly do you have the figure for work? Like how is it, and what is it going to be, and how does it change?
Well, it looks like this right here. All right, so let me actually go to our Blackboard page to see where are we. No. The course information and equation sheet.
I know the equation for it is force times distance.
Okay, all right.
Do you apply it to this problem?
Okay, so in this problem,
So
we're going to have, like, in order to see the friction force, though, we kind of have to do a little bit of, like, I guess we could just draw it in there. Right? There's a friction force. I guess I'll be red, like that. Right? And he acts along that whole thing. Right? So as this thing moves from here to here, he always has a force that's pulling against him. And so that's the external work.
I get it. So I'm saying, so like, how, so it could be found the friction force is 22.07 million.
Yep.
So if you apply it to the equation for work, which is force times distance, how exactly are you going to find that distance? That's like, I'm going to get stuck right there.
No, because we know this distance over here.
Oh, so you use open.
So we're just what we're gonna do is because these things are literally tied to each other, right? We're gonna make some equations. So I needed to do that over to the side. Even on my page right here, I kind of do them over to the side. Kind of like little side equations I go. And a lot of times for me, I literally do that, you know, I might recognize ahead of time that I need it, but most of the time it's like, I get to a spot like you're describing and I get stuck and I go, oh, I know what I need to do. I mean, I literally do that. I say, oh, I know what I need to do. I needed to find out some relationship between here. So if I wanted to find the distance that, let's say I want to know the angular distance that this thing moves, right? I would say that I'd have delta YA is going to be my delta theta times my RO, right? Or the angular position change of this thing.
Yeah, they will plus RO.
Is going to be the delta YA over RO, right? Does that make sense?
So delta Y is okay, it's change in height.
Yeah. So this thing moves this amount. This cable unwraps from here, makes this cable wrap around there. I want to go, how many radians is this thing going to rotate when that happens? And that's going to be 0.9 divided by 0.25. So something less than, oh no, I guess it's more, okay, 3.6 radians. So really just a little more than one turn. No, a little more than half a turn, right? Because each revolution is 2 pi radians, so that's just a little bit more than pi. So it's a little bit more than 180 degrees. So now you also will want to know, well, what distance now is this thing going to move? Well, it's going to be the same kind of like concept right here. Right, so how much cable gets wrapped up around here in that many rotations? 3.6 times 0.15. And we end up finding it's 0.54 meters. We could call this kinematics, I guess. This is really dependent motion. Maybe we would actually call that part of it. Oops. Let me cross it out. And while we're here, we also have some kinematics that are almost identical to the thing, right? We could say that the velocity of A is equal to omega times RO, right? And then the velocity of B is equal to omega times RI. So later on, we're going to want to do that when it comes to the kinetic energy. So much fun, juggling. Okay. So back over here, we'll say that the work that's going to be done is going to be negative F friction times delta XV, as we described it. We'll say 22.07, and we said this thing was going to move 0.54 meters. So a negative 11.92. I don't want to put parentheses. The kinetic energy at state 2 is going to be all three kinetic energies. So 1/2 massive A VA2 squared plus 1/2 IC times omega 2 squared plus 1/2 MB VB2 squared.
So,
And I know I didn't get the in between numbers. What? Go ahead.
so what you just wrote there and look here. So is the first portion, the MA, the 1/2 MA, not gonna be 0 since it's after it hits the ground.
No. This is just before it hits the ground. Yeah. So maybe we could even put a itty bitty tiny little gap in between there. As soon as it hits the, right after it hits the ground, it's gonna stop. We're not down. That's difficult.
So then that's when you use the kinetic relationship for the velocity.
So here we go 1/2 11.5. I'm going to stick with VA just because that's what I have on my page. Plus 1/2 0.3812, and then for omega 2, I can put him right here. So I can go omega is VA over RO. And then I can also put this back into here and say VB is equal to VA RI over RO. Yes. So what we're able to do right here is say VA2 over RO, which is 0.25 squared plus 1/2 of 9 kilograms. And then I have VA2, and then that's going to be 0.25. No, it's going to be 0.15 and 0.25 squared. And I do have the in-between number here. That's 10.42 VA2 squared. So I can apply all of these together. There's reflection. I wonder if there's light. I wonder if half these lights are going out. Nope. What about these then? Nope. Anyway. And then PE2 is going to be 0. Let me say that. PE2 is 0. So we go 0 plus 101.5 minus 11.92 equals 10.42 VA2 squared plus 0. So we get VA2 is going to be equal to 2.933 meters per second. And then also from this, we can find that omega 2, let's call it, is going to be 2.933 divided by 0.2550. Two point nine three three 0.25. So we get that this is 11.73 radians per second. We'll also find that V2 is going to be our 2.933 times 0.15 divided by, or actually I just could have just multiplied this over by, so 0.15 times that, and I get 1.760 meters per second. But now we've only got up to this spot right here. We want to now find out what distance this is going to move. So we want to move from 2 to 3 now. And I wish I had a longer USB cable to be able to see this a lot better. So I get the kinetic energy at 2 plus the potential energy 2 plus the work done 2 and 3, kinetic energy at 3 plus the potential energy. But that's pretty good. The kinetic energy at 2 does not equal the kinetic energy. But I got to be careful here. I might have wanted to say an in-between step here. I might have wanted to number these differently. Like maybe I want to make this one 4, and 3. This is before impact, and this is after. Right? And so then therefore I want to change all of these things. Sorry about that. So I'm going to go stage 3, go 3 to 4, and 4. So at stage 3, I no longer have A as part of my setup. A is gone because it's hit the ground and the cable's slack. So it no longer influences what's going on. It's purely the momentum of both the cylinder and the lock together. Here's 1/2 M, I guess I'll go with B first. B, VB3 squared plus 1/2 IC omega 3 squared. But these are also, these will be, nothing has changed here, right? So these are, this is omega 3, and this is VB3, right there. There's no reason for them to. So that's 9, and that's 1.760 squared plus 1/2. I'm going to make a test of something here in a second too. 0.3812 omega 3 is 11.73. I've actually in my head I've just made this a much more complicated problem. I don't know if I'm going to regret it, but that's okay. But all right. So it's 11.73 squared. So I have 40.16 Newton meters is the kinetic energy. And the potential energy, state 3 is equal to 0. The work done between 4 and 3, 3 and 4, is going to be that friction of B times delta x B, and there we go, 3, 4. Right? This is it kept moving. And this is really what we're going to solve for, right? So this is a negative 22.07. And this is what we're looking for. And then KE4 is equal to 0. It's going to stop. VE4 is equal to 0. So put them all back into the original thing right here, and you get 40.16 plus 0 minus 22.07 times delta x b 3 to 4 is equal to 0 plus 0. So our delta x b 3, 4 means he's going to keep on sliding. .820 meters. And so that would be the kind of problem where we do, where we show 2 stages. Now the thought experiment that I have here was, what if the momentum of B is so much? Is that possible? Is it possible that this will stop rotating and this will keep on moving? And I don't think so. I've had the same, I recall having the same, like, say it again? Okay. So, this thing has angular momentum, right? It has kinetic energy, the disk, right? This piece. And he's rotated, and then he's being pulled to a stop by him. And this has linear kinetic energy. It's all kinetic energy is the same, but he's got kinetic energy just because of his translation. And so he's going to keep being pulled by him, right? So you almost have to kind of think of it as being 2 parts going on, right? So we have a force of attention right here, and then we have force of attention right here, right? These 2 things. And this guy, he's got kinetic energy, but he's being robbed of the kinetic energy because of that tension that's pulling up against him. And this guy, he's got force of the friction that's trying to stop him from going in that direction, but he's also got the tension because of this guy, right? They're interchanging at the same time. There's 2 things going on. There's a tug of war going on in one respect, because he's got this kinetic energy that wants to keep rotating, but he's being pulled back by that tension in the rope, which is, really in a lot of ways directly connected to that friction. But I got to remember, you could do this in Newton's second law as well, right? We could draw these have decelerations taking place, which is actually a really excellent problem to do in Newton's second law as a demonstration of this. Right? So you could say at the same time for this problem, I don't mean to make it more complicated, only to explain it. So, So we have reactions right here and a weight that's coming down. I should run it on the side, make it smaller to fit underneath. Well, we have the other forces in there, I just don't want to leave them off. But this is the only one that matters because we're going to do it rotationally. And he's going to have an I alpha right there, right? Because he's slowing down. He's decelerating. We have the force of the tension on the block, right? So that's if we cut the cable right there. We also have the friction force down, and I didn't leave myself enough room to. I'm making a mess now. For the normal force and the weight, that kind of thing. And there's a mass of 3, right? Acceleration is it. But I'm just trying to show that these things are interrelated to each other, the two. And I want to know, is there a scenario possible? And I'm asking this without knowing the answer 100%. I'm not 100% convinced. When this guy will stop, but this guy keeps on going until the friction's enough to stop it. And I don't think so. But I kind of want to try to do like a couple of experiments to kind of, maybe, or not experiments, but maybe a couple of calculations on the side. I'm trying to think of it as a way that I could rationalize or make like a test for myself. This is not part of the exam. This is me just trying to think my way through a problem of is it possible? What if? Hypothetical.
I mean, the answer has to be no, because for that to happen, the way I see it, for that to happen is your weight of B would have to be like something small, and like if you have the smaller your weight for B is, to be honest, the less friction matters.
Yeah, what if the friction was really, really small? Like, what if this thing was on ice, right? It would still eventually stop, but this wheel, for as long as this thing is providing some amount of resistance, right? That's going to keep this. That's going to keep the. I think what I would do here instead would be make a test, right? So we have an answer already over here, with the assumption that they're tied together and they stop at the same time. That's what this assumption is right here. That kinetic energy, which we've lumped together, and this right here they're going to stop at the same time. And my question is, well, this has its own kinetic energy, like right here. And when it's going to go through, trying to think about how to say it right here. I could try to find out from an FBD, I could find out what the tension is going to be, because the tension is going to be, is it going to be constant? I think the tension is going to be constant because the forces are constant. There's no reason the accelerations are constant. There's no reason the accelerations would change. Like there's no reason the forces would change. So I guess maybe the test that I would do is to find the tension and then find the distance it would take for this kinetic energy. It's really this competition between these two right here. That would be the test that I would make to see if this distance is enough with that tension to cause that thing to stop early, right? Yeah, I could do that. I could use that tension and this distance and test it to see if there's any chance this guy's going to be enough to slow this down completely for this one to keep on sliding until the friction decides to let him go. It's an interesting problem. It's too complicated, but
I think it also lies in the velocity of that wheel, because that's where it starts, and that's where it's going to have to end.
I wouldn't disagree with it. But I think I would just want to say that it's all literally connected to each other, right? They're interdependent on each other, and it's really the magnitudes of the moment of inertia, the magnitudes of the velocities. I don't know. Actually, those might not play as much of a part. But that coefficient of friction, so the magnitude, the coefficient of friction, is going to influence, and also the mass of B, right? If the mass of B is big or small, that'll make some decision.
We have the omega and the velocity of B right here, and we set up their constant. So your trade-off here is 11 radians per second versus 1.7 meters per second. So
Yeah.
block B.
It's about their kinetic energy. It's like right here, you know, there's part of here's some kinetic energy due to that. Here's kinetic energy. But that kinetic energy is going to be dissipated because of this friction and that distance.
Yeah, that's what I'm saying. Like because like you look at your starting initial values, your making your velocity. The difference between them is too big, and then if you're counting friction, then you see what I'm saying?
I do. I think I see what you're saying, but I would still. I'd want to. I think there's a way that it's possible for the thing to keep on moving, for B to keep on moving when C has stopped. I don't know. I'll mess around with it at some point. It's good. Good thought experiment. All right. Do you need to see a Newton's second law problem?
Yes. But isn't just that right there, the FDD and IBD?
Yes. But this is, one of those is a translational, one's a pure rotation. The difficulty with an FB for Newton's second law can arise when it's not about a fixed point, when you have both translation and rotation happening to the same body. I had one homework problem where it was like that, I think.
The day feels so weird.
Why?
Nothing else to do, like. So used to going.
I'm getting hate mail because I have to have exams prepared. Supposed to have exams prepared early. Let me see if I'm still recording here. I think I should be. Let's see. Zach is still here, or logged on. I don't know if it'll stop recording automatically or if it'll keep on going. We'll see. All right. Yeah, I don't have any of those problems. I think this is about the only problem here.
So much of the static.
It seems like a stacks problem. But see, this thing is on a flat surface, frictionless flat surface. So this is like you think it's a hockey puck kind of problem. I don't know, hockey puck problem. You think of it as a, I don't know, like, it's this right here. May go and push in that. All right, so it's going to translate and it's going to rotate at the same time, right? But now we're saying friction. That's not frictionless. So put those forces on. center of this thing. And I may not have already done this, so 3 meters there, and 0.75. I feel like I did this somewhere. Does this seem mass of the thing is 100 kilograms? The force is 500 newtons. And we're going to find acceleration B.
Stuff I find in I first.
Definitely.
So, cinder rod is 112 mass times length.
You got it. Square.
The length is for, yeah.
Can't do it in my head. Well, it's going to be 900 divided by 12, right?
Oh, yeah.
75? And we're going to have to do an acceleration analysis, a kinematic analysis, but we'll see that here in a second. But we'll start off with the most important part of the whole course, the FBD and IBD. I guess we decided to go that. Right? I think this is Y and Z. I don't know why we do that. We'll look at X and Z. And this was 500 newtons. We're looking at all the other forces that are onto this.
I just have the force and the mass.
Say again?
I just have the force and the mass of the bar. That's what the all the forces. And then, that's about it. Because there was no ground.
There's no other force on here, right? Because we're looking down on it.
You gotta go and include the weight.
This is acting down. Y is out of the board. This is on a flat surface. Got no. So, what we have to do is go mass times the acceleration on the center of it. We also probably anticipate we're going to have I alpha. So what we can do here is take the sum of the moments about the center of mass equal to the sum of the moments about the center of mass effectively. But in this case, what you can do right here is, because this is going through the center right here, that's really just going to be I alpha. So what you can find is, when we're taking counterclockwise is positive. So you go 500, because going counterclockwise is about the center right here, times, and this should be 0.75 right here, right? And from here, you're going to be able to get 75, and you get alpha. So we'll be able to find alpha. So 500 times 0.15. So alpha is just going to be 1, all right? Okay, 0.75. Yeah, I go 0.75 times 500. Okay, maybe I screwed up. 500 times 0.75. I tied the wrong thing. All right, so divided by 75. Sorry, the other one is 5. 5 radians per second squared. Now we take the sum of the forces in the z direction is mass times acceleration in the z direction. So they say, and we'll decide if that's positive. 500 is going to be equal to 100 times AZ. So AZ is going to be 5 meters per second squared. Okay, did that right? So now what we were trying to find was the acceleration of B, right? So what we do is our 3 diagram method. So all we know right now is that right there is 5, right? Let's call this the acceleration of G. I was thinking B, sorry, right? B, acceleration of G. We want to find the acceleration here, so let's draw the acceleration of B in that direction. What we do in this diagram is we apply the acceleration that we know to the spot where we want to know, and then we pin it right here. And we know that its alpha is going that direction. So here's the acceleration of B with respect to G in the tangential direction. Now this thing's starting from rest, so there is no normal direction. There's no acceleration in the normal direction like we had previously done. So we can simply write the acceleration of B to be equal to the acceleration of G, if that's our reference, plus the acceleration of B with respect to G tangentially, plus acceleration of B with respect to G in the normal direction, fortunately that's 0. So all we need to do is for the Z direction, because that's the only one that matters to us. Z dir.
It's the acceleration of G is not going to be alpha times the distance, right?
Nope. Right here, sorry. right here is going to be acceleration times L/2. But this happens to be the negative z direction, that direction right there, right? So that's why that's going to be minus 5. There's 1.5. Right? So we're going to have a negative 250. 2.5, sorry. Does that make sense? So it's this thing right here. It's going to be slightly like when it's accelerating. It is accelerating that direction. It's rotating that direction. But this guy, because it's not being pushed to the center, is kind of actually accelerating that way. Right? This guy, not as much as the center. So it's like kind of like going like that. Which I guess kind of makes sense. All right, I gotta get going home soon but do you have any more questions, do you think? All right. Well, do your best to get as much work as you can in when you can. Of course, balancing with your other courses, but make sure you get some sleep. Do not try to do an all-nighter. It does not make practical sense.
Just forget everything that you try to memorize.
Because so much of doing the work is trying to organize your thoughts, and it's very, very difficult to organize your thoughts when you're running on not enough sleep.